So, again, going back to our illustration of a binary system, there they are on orbits that are the same shape but different sizes, both going around the center of mass. The line between them always passes through the center of mass instant by instant by instant. And furthermore, the position of the reduced mass in its orbit around the system mass, big M at the origin, is always the same as the position of mass 2 relative to mass 1. Now, which one you call mass 2 and mass 1 is up to you, but typically we make the smaller mass M2, and so if this is M1 and this is M2, then, I don't know if there's some, yeah, they're all, spacebar did it, okay. Then at this moment, the position vector of mu is this vector right here. From M1 to M2, that vector right there, move it over to the origin, that is the instantaneous position vector of mu. A little later, the position vector of mu is this vector, shifted over to the origin. So take all of them and shift them over to the origin, and that itself will trace out an ellipse, which has a semi-major axis equal to the sum of the semi-major axes of the two orbits. We would just add them together. So at this moment, here is the position vector of u. Take that vector, move it over to the origin. You just do that. At every point, you keep taking that relative position vector, move it to the origin. What do they trace out? They trace out the relative orbit, which is an ellipse that has that same eccentricity, same shape as either one of the two ellipses, but its size is the sum of the sizes of the two ellipses, or in other words, its semi-major axis is the sum of the semi-major axes of the two ellipses. Does that make sense? Yes?
So if you wanted to go back to a two-body, could you do that?
You can, yeah. We're gonna write down the equations that basically tell you, okay, if I know the parameters of the one-body problem, here's how you translate that into two-body quantities, and you can go backwards too. You can invert it, as long as you, you can invert it, because if you know the system mass and the reduced mass, that's two quantities, and there's two unknowns, M1 and M2. So you can always invert and solve for what a given value of mu and m uniquely specifies M1 and M2, and vice versa. So you can always go back and forth between the two descriptions. Yes. Mm-hmm. Meanwhile, it's so fun. Whee! I'm running out the curve. Damn, I ran out there. Not quite enough.
M2 and
Whee! The viewer can put in their own sound effects.
Yes, sound effects not included.
Sound effects not included, that's right. All right, let's zoom out. Let's zoom out here and go back to our story. Yeah. And now I will make it absolutely impossible to pay attention to what's on the board, because the video is going to have that happening the whole time. And it's kind of hypnotic. So I don't know if you guys will be able to pay attention to me either, but I'm just going to leave it there to keep making that impression. So I wonder if I can grab one of them.
You got it.
No, doesn't seem to work. All right, anyway.
Only there were pieces of junk.
Yeah. It's garbage.
Shit.
Okay. Now, so, as I was asserting there, and you kind of imagine from looking at that, the relative orbit, the orbit of mu around m. So in other words, there's m fixed fixed in place by magic, space-time nails, space-time nails. There's mu. Mu orbits M on the relative orbit. The relative orbit of mu about M. Where was I? Yeah. As A is equal to A1 plus A2, and E equals E1 equals E2. So the relative orbit is bigger than either orbit alone. In fact, its semi-major axis is the sum of the semi-major axes of the two orbits around the common center of mass.
Is that E?
It's E. Yeah, E, the eccentricity of the relative orbit is the same as the eccentricities of the two individual orbits, which are the same anyway. So for these guys right here, the relative orbit would have a semi-major axis whose length was that plus that, the sum of the two semi-major axes. So it would have exactly the same shape, but it would be a bit bigger, because it would be the sum of the sizes, if you will, of the semi-major axes of the two orbits. And as we'll see, it's a great simplification to only have to keep track of mu. And again, you can always, if you know where mu is, you can figure out where M1 and M2 are. You can always go backwards and forwards each way. We've put the center of mass at the origin. Capital R equal to 0. We have, as we asserted before, M1R1 plus M2R2 is equal to 0. Again, the center of mass has the denominator being M1 plus M2, but if the whole ratio is equal to 0, then the numerator is equal to 0. So we only need the numerator. M1R1 plus M2R2 is equal to 0. But remember we said that R is R2 minus R1. So that says that we can write that R2 is equal to R1 plus R. So let's substitute that in above. So that says that M1R1 plus M2R1 plus M2R is equal to 0. Just plugging in R2 is R1 plus R in the expression of the center of mass is the origin. So now we can write that R1, because now we've just got R1 and R in our expression, so we can put R1 in terms of R. R1 is equal to minus M2 over M1 plus M2 times R. And so this is doing as promised. In other words, if I know the value of R, and I know M1 and back to the original two-body problem. If I know where R is, I know where R1 is. So here I just solved this for R1. This is M1 plus M2, the quantity R1, plus M2R is equal to 0, so then I just divide through by M1 plus M2 and write that R1 is minus M2 over M1 plus M2R. And we have that R2 is equal to R1 plus R. One way to get it, there's more than one way to get this. So if we write all that out, well, now we know that R1 is equal to minus M2 over M1 plus M2 times R. So we can write this as M1 plus M2 over M1 plus M2 minus M2 over M1 plus M2 times R. What am I doing here? Yeah. Right. So in other words, here I just put in that R1 is minus M2 over M1 plus M2, and here I've just rewritten R as M1 plus M2 over M1 plus M2 times R, so that I can have them over a common denominator. I'm just reading, in other words, that first one is obviously 1, but I'm putting over a common denominator. And so now I can add numerators, and I get M1 plus M2 minus M2, which is just M1. So in other words, R2 is equal to M1 over M1 plus M2 times R. And it makes sense that one of them has a minus sign and the other one has a plus sign, because remember, with the origin at the center of mass, the two position vectors have to be going in opposite directions. So one of them is going to need the minus sign and the other one's going to need the plus sign. But a better way to write this is to use our definition of mu. With mu being M1, M2 over M1 plus M2, that was our definition of mu, we thus have that we can write R1 is equal to minus mu over M1 times R, and R2 is equal to mu over M2 times R. And that's what I'm going to draw the box here. That's the probably more useful relations, which are entirely equivalent to what we have over here. So these are the two relations where if I know what R is, I can then figure out what R1 and R2 are. The equivalent one-body problem wouldn't be very useful if you couldn't translate it back into the original two-body problem. But wait, there's more. Let's rewrite the energy. Okay. Now we rewrite the energy. OMGZ! I am so excited. How to make class pseudo-exciting, no matter how much, right? No, this is good stuff. It is actually good stuff. I like this stuff. So in terms of the one-body problem, energy will be the sum of the kinetic energies plus the mutual gravitational potential energy. So, what's the generic expression for kinetic energy? 1/2 m v squared. So there will be a 1/2 m1 v1 squared and a 1/2 m2 v2 squared. And so this is in the one-body problem, just from first principles. And then the gravitational potential energy is minus g times the product of the masses divided by the distance between the masses. And the distance between the masses is the magnitude of the vector r2 minus r1, because r2 minus r1 is the vector connecting the two bodies. So the distance between the bodies is the magnitude of that vector, r2 minus r1. Any questions? Now what would be nice is if the formula for the energy is also what you would just get if you had big M and mu interacting. And since big M is fixed, all the kinetic energy belongs to mu. So you would want it to be 1/2 mu v squared minus g big M mu over r, the distance between them. Let's see if that works. And it does, because why would I be doing this if it didn't work out? But from above, we have, if we look at our expression for R1 over there, take a dot. We have R1 dot is equal to minus mu over M1 times R dot. Or in other words, that V1 is equal to minus mu over M1 times V, where V is that relative velocity of mass 2 relative to mass 1. And similarly, R2 dot is equal to mu over M2 times R dot. So that says that V2 is equal to mu over M2 times V. So notice that the R's and the V's essentially have the same relation to one another. In other words, R1 is minus mu over M1 R. V1 is minus mu over M1 V. And similarly for V2. The V's and the R's have the same relation. Put another way, the ratio of the velocities, of the speeds, is also the reciprocal of the ratio of the masses, just like the ratio of the distances from the center of mass is the reciprocal of the ratio of the masses. This is all if you put the origin in the center of mass. If you put it on Alpha Centauri, stop. It's different. Don't do that. Back up. Back. Don't put the origin on Alpha Centauri. Or Sirius. Bastard. Yeah. Or Canopus. Or 3 inches to the right of the center of mass. None of those. They're all bad. So, okay, over here. We can say that E is 1/2 M1 V1 squared. Well, V1 squared, when I square it, when I just take magnitudes and square it, or dot it with itself or whatever, that'll just be this whole thing squared, so mu squared over M1 squared V squared. So 1/2 M1 times mu squared over M1 squared V squared. And similarly, 1/2 M2 V2 squared, well, V2 squared is just mu squared over M2 squared, V squared. V again being the relative velocity. And then for M1, M2 over R there in the gravitational potential energy, there's nothing stopping me from rewriting it as G times M1 plus M2 times M1, M2 over M1 plus M2, because then the M1 plus M2s just cancel each other, so I haven't like undone anything, times 1 over R, where by R I mean how far apart the two masses are, because that is the magnitude of R2 minus R1. And in fact, note that because of the way we've set up the equivalent one-body problem, the distance from M1 to M2 is the distance from mu to M. Because in the equivalent one-body problem, the distance from mu to M is the same as if you were riding along with mass 1 and seeing where mass 2 was at all times. So those are the same. The distance from mu to M is the same as the distance from M1 to M2. The relative displacement we set is the distance from M to mu in the equivalent one-body problem. Any questions? So let's rewrite up there. So this is, each term has a mu squared in it, so we've got 1/2 times mu squared times, this is m over m1 squared plus m over m2 squared. So that's 1 over m1 plus 1 over m2 v squared. Because in this first term we've got m over m1 squared, that's 1 over m1. In the second term we've got m2 over m2 squared, that's 1 over m2. Minus, and then, what do we call that? What's m1 over, m1, m2 over m1 plus m2? That's mu. And what is m1 plus m2? Big M, that's big M, that's the system mass. So notice that's G m mu over R, which is exactly what you would get for the gravitational potential energy between masses big M and mu. So we get minus G m mu over R. And the other thing to realize is that 1 over m1 plus 1 over m2 is in fact 1 divided by mu. That is 1 over mu, because 1 over mu would be m1 plus m2 over m1 m2, right? Mu is m1 m2 over m1 plus m2, so 1 over mu is m1 plus m2 over m1 m2, but that's 1 over m1 plus 1 over m2. Going back to how we said that when you're doing the reduced mass, the reciprocal of reduced mass is the sum of the reciprocals of the masses, just like when you add resistors in parallel to one another. The reciprocal of the equivalent resistance is the sum of the reciprocals of the resistances. So by cosmic coincidence, that works the same way. So E is equal to 1/2 mu squared over mu v squared, or in other words, 1/2 mu v squared minus Gm mu over R. But that's exactly what you would get for if you had a fixed mass m having a little mass, having another mass mu orbiting it. The gravitational potential energy would be minus Gm mu over R, and the kinetic energy, because big M is fixed, all belongs to mu, and it would be 1/2 mu v squared. So in other words, wow, you get exactly what you would expect for the equivalent one-body problem. It gives you exactly the same result as the real two-body problem. Ooh, ah, just what we would expect.
Ah.
Ooh. Or you could do that too, I'd be equally happy with that, yes.
Ah. Oh.
Where you just, ah! Which of course is a delighted scream. So, you get just what you would expect for the energy for mass m interacting with mass u, and mass m being fixed. Wow! Let's see if the system's angular momentum works out to what you would expect too. You know what? I'll bet it does.
Whoa.
Yeah.
This is a pretty bold claim.
But you know what? I can back up those claims. For the system orbital angular momentum, we have, so first of all, we need to remind ourselves that if I have an origin, a particle of mass m, moving at velocity v, and its position vector is r, the angular momentum, so the L for angular momentum makes a little more sense because there is an L in angular. The angular momentum L, and of course we use often N for torque because anyway, L is equal to what? Do you remember? What's the definition of the angular momentum L of a particle of mass m with position r, vector r relative to our origin, and velocity v? The angular momentum is what?
P cross R.
Almost. Other way around. R cross P. R cross mv, which is R cross P.
It's so simple that
So L is R cross P for angular momentum. So fundamentally, for the two-body problem, it'll be the sum of the orbital angular momenta of the two particles. So that'll be m1 r1 cross v1 plus m2 r2 cross v2 And now if we use those relations that we derived before, then this turns into minus mu r cross v1 plus mu r cross v2. And that, again, refers back to our earlier relations that r1 was minus mu over m1 times r, r2 was mu over m2 times r. So therefore, if I look at m1 r1, that's minus mu r, and m2 r2 is mu r. So I'm just plugging those into that relation. Oh, but wait, we can write this as mu r cross v2 minus v1. But v2 minus v1 is what we're calling, I know there's lots of things here. v2 minus v1 is the velocity of mass 2 relative to the velocity of mass 1, which we are calling the relative velocity, and using the symbol simply v, just plain v, the relative velocity. So this is mu r cross v. Or, if we pair the mu with the v, we can call this r cross mu v. And if we call mu v little p, then we get that L is just r cross, L for the whole system is just r cross p, where p is the momentum of mu in the equivalent one-body problem. So where p equals mu v is the momentum of the reduced mass. It is not the system momentum. Since that is zero by definition in the center of mass. Remember, the system momentum, capital P, would be the system mass times the velocity of the center of mass, but we're in the frame where the center of mass isn't moving. So P equals mu v is the momentum of the reduced mass in the equivalent one-body problem. It's not the system's momentum. But in other words, ooh, that works out too. The angular momentum is what you would get for the one-body problem with little mass mu moving around with velocity v and momentum little p. R cross that would be the angular momentum of the system. So the energy works out like it should, the angular momentum works out like it should. I mean, everything's just awesome is what it comes down to. How great could life be? It couldn't be any better. Well, I mean, it could, but still, it's great. Any questions? I'm deciding which one I want to do first, Kepler's second law or Kepler's first law. Probably Kepler's second law, because it's actually quicker to derive Kepler's second law than it is to derive Kepler's first law. So, let's derive Kepler's second law, shall we? How exciting is that? I know, exactly, yay! Right, so, Kepler's second law. I could click this to get an animation from the web. How awesome is that? So Kepler's second law, line, doesn't have the link. Okay, I'll go to my Astronomy 111 slides. Where am I? What am I doing? Going to my Astronomy 111 slides. I just said so. But I've been lecturing for a long time today. And so I'm almost out of neurotransmitters in my speech center. And that's when I'm
Reaction potentials.
That's right. My action potentials kind of got up and went, retired. Is that what
My action potentials are on strike.
Yes, that's right, yes.
Brian Jones. Physics jokes.
All in one. How very Finkian of us.
Hey,
Yo. Let's
Hey.
see. It was pretty similar to
Hey,
ours.
Joe.
Let's see. Wait, where's the up-to-date version? It didn't save it. I'm in the wrong place. Oh, that's tragic. Need to fix that. No, we should still work with this one. No, what are you doing, loser? Oh, this one, okay. Still, it's supposed to be this number. Okay. Boink. Fun, huh? Kepler's second law. Ooh. Ah. Equal areas and equal times. Why, even if I go to like Pluto. Yes. An object orbiting the sun. A dwarf planet. Right? It's gotta move faster and faster as it gets closer to the sun because, you know, if a mathematically inclined chef made elliptical pizzas and decided to slice through a focus of the pizza but wanted everybody to have equal area slices to make everybody happy, then our chef would need to have short fat slices and long skinny slices in order to make them all have the same area. And so in order to obey Kepler's second law, the planet needs to be moving faster when it's closer to the sun. And if we really dial up the eccentricity and say go, then again we see whee! That's fast. Yes. So, it turns out that Kepler's second law fundamentally is an expression of conservation of angular momentum. That Kepler didn't realize that, but Kepler's second law is actually expressing conservation of angular momentum. And so what we want to do is show that in fact, Kepler's second law is an expression of angular momentum conservation. Let's do that, shall we? Or at least get close to doing that. Derivation of Kepler's second law. Kepler's second law is at its heart a statement of conservation of angular momentum. Conserve. It's doing such a good job of it. From above, if we take the derivative of r cross p, L dot is going to be r dot cross p plus r cross p dot. Because you can use the product rule for cross products. Derivative of the first times the second plus, or cross the second plus the first cross the derivative of the second. So that'll be V cross P plus R cross F, because R dot is P and P dot is the force, F. But V and P are parallel to one another, because P is mu V. If two vectors are parallel, what's their cross product? 0. So that term is 0. And for gravity, F points in towards the origin, opposite to R. It's pointing in the opposite direction of R. If two vectors are anti-parallel, pointing in 180 degrees apart, opposite directions, what's their cross product?
0.
0 as well, right? In other words, L dot equals 0. So far what we've shown is that the angular momentum is constant for a central force like gravity. Gravity conserves angular momentum. L dot is 0, which means L is a constant. That'll be true for any central force, any force which points towards or away from the origin directly. It doesn't have to be inverse square law. So now, let's show that in fact the rate at which area swept out is actually proportional to the angular momentum. And since the angular momentum stays constant, that means the rate at which area swept out stays constant, and that is Kepler's second law. So consider the following. There's our elliptical orbit. There's the focus. There's M at the focus. Cute little mu orbiting it. Let's say the distance is r. Actually, I'll put it, doesn't matter really, but I'll put it over here. I think the r can be either one. We're talking about a very narrow slice here. So in the limit, as d theta goes to 0, so that those two radii are closer and closer to being the same length as one another, then the idea here would be I can drop a little perpendicular there, and to a very good approximation, the length of that perpendicular is r times d theta, just from the definition of radian angle. R d theta is that little length right there. And that area swept out in going between those 2 points, as long as theta, d theta is very small, looks like a long skinny triangle, does it not? I mean, one edge is curvy, but as you get narrower and narrower, the curviness of the ellipse becomes less and less important. Area swept out is a skinny triangle, almost. With area, we'll call that dA, because it's a little area, a little differential element of area, equals base times altitude. So actually I will base times altitude. Well, the bases are, the area of a triangle is half of the base times the altitude. Rectangles, parallelogram is base times altitude. Triangles, half of base times altitude. So the bases are, and the altitude is r d theta. So dA is 1/2 r squared d theta. And sadly, it's time to stop. So you'll have plenty of time to forget what we were doing by Tuesday. I'll have to remind you a little bit of that, and then we'll proceed from there and get the very cool result that Kepler's second law is actually angular momentum conservation. It's a way of expressing that. Kepler had no idea. But it's one of those, I wonder how he thought of that.
Little did he know.
Little did he know.